if you talk to companies that have been working in ground penetrating radar for years, they almost always say, no, that wouldn't work.
From EE Tech and All About Circuits, this is Moore's Lobby. I'm your host, Daniel Bogdanoff. Today in the lobby, we're going underground to look at a unique sensor approach to autonomous driving. You've probably heard a lot about LiDAR and camera-based sensor systems, but GPR is using ground-penetrating radar to look beneath the road surface at the Earth itself to help autonomous vehicles navigate. I'm joined today by GPR's VP of Strategy, Noah Gedrimas. Noah, thanks for being here today.
Yeah, thanks for having me.
I'm curious, how did you first get into engineering and tech, and what do you enjoy about it?
Yeah, so engineering and tech, I think it's the most open-ended aspect of science there is. Everything is continuously being improved and changed. Your job's always changing as an engineer, which I love. I love that, 2 years from now, I'll be working on something completely new and completely different. And, engineering is this field of making decisions with incomplete information constantly. And I really enjoy that aspect. I like the building and the complex problems and, working with smart people, and engineering is just full of that.
Have you always been a car and automotive buff, or is this a new space for you?
Yeah, I mean, not just cars. I really like, my wife makes fun of me. It's vehicles. It's not just cars. So I have, tractors and farm equipment and construction equipment, four-wheelers, snowmobiles, pretty much any kind of a vehicle I find appealing, but it's really anything mechanical, even tools and things. So from a pretty young age, my aunts and uncles say that I was taking things apart, when I was only 5 or 6 years old. Just always been interested in how things work. So that a lot of that came out of my dad and his business, learning how to work with my hands. And so yeah, as long as I can remember, it's been really interesting to me how things work, how to make things better, and how to build things.
I would always take things apart, but I could never get them back together. That was my big challenge.
There was some of that for sure. There was definitely some of that. I remember just my parents' house having all kinds of stuff torn apart, and then a long time, if never, getting them back together. But I think more often than not, though, that's one of the things I tell my friends that are maybe uncomfortable, fixing their own transmission in their car or something, is tear it apart. You'll figure it out. You'll get it back together. I think a lot of times people get kind of scared by, I'll never get this back together. I don't know how exactly, but somehow it always comes back together.
Yeah, I just did my alternator and I was very excited to have no leftover bolts when I was done.
Yeah.
It's like, okay, we did it. What got you started in autonomous vehicles?
In undergraduate, I was really big in a program called SAE Mini Baja. And this is a project where you build this like little off-road dune buggy and you race it against other schools at the end of the year. So all the engineering schools. And I really liked that, got really involved with that, and then had a connection to Virginia Tech. I went to a school called Rowan in New Jersey, and I landed an internship at Virginia Tech. And the scope of the internship was I was supposed to build a 1/5 scale car for automated parking, so for like self-parking. But I was just going to build the hardware, so put like a little electric motor and build the chassis with the Ackerman steering and the same vehicle dynamics as an Audi A8, but 1/5 scale. And then the graduate class would program it for the robotics class. Well, I had the whole summer to do this internship, and I built the chassis in about 2 weeks. It didn't take me very long to build this chassis. And then I had the rest of the summer, and I asked my professor, like, well, what do I do now? He said, why don't you try to program it? So then I, at that point, no experience in anything mechatronic or robotic, started calling up like Pololu and SparkFun, the companies that sell all these things. And I started learning about mechatronics. And over this summer, wrote my own algorithm to park the car and have my own MATLAB simulator. Remember, I had in this lab at Virginia Tech, I had a camera on the ceiling, and I had a MATLAB sort of scripts that would do camera tracking so I could create motion models. And by the end of the summer, I learned how to program, at least within Arduino, to get this car to park. And actually, I have a YouTube video of it. It was one of the first YouTube videos I ever published, and lots and lots. I think it has over 10,000 views, which is a lot for how silly of a video it is of this thing parking. After that internship, I just had this newfound respect for mechatronics and robotics, and just how easy it is to get things to do really complex maneuvers, where if you wanted to do, things with 4-bar mechanisms and more traditional mechanical engineering I was familiar with, it's so much harder. And that really kind of struck the autonomy for me. Yeah, and what was cool about that internship too was it was at Virginia Tech's, I think it's called VTTI, Virginia Tech Transportation Institute. So they do a lot of crash testing there. And the machine shop where I would machine these parts, it was in the crash sled area.
Yeah.
And what Virginia Tech would do is to study the effects of crashes on the human body. They would get actual cadavers and put them in this crash sled. And when I say, I was working in a machine shop less than 50 feet away from this. And they would crash the sled, and then they would do autopsies. So all the students would do autopsies and see the effects of what an accident would have on the human body.
Whoa.
Hugely distracting, when you're trying to yeah. But it was really cool to see how detailed they get into in the effects of airbags and seatbelts and all these things. And it was really cool, the machine work too, because before I saw it run, I thought that it would be it was maybe 200 feet of track, steel track, and there was a car on it with all the seatbelts and the seats. And I thought it was going to get up to speed and then crash into a wall, but it was actually the exact opposite. They had all the cameras and everything set up on one side and a big pneumatic piston, and then they would basically punch the sled, and then the sled would slow down over 200 feet.
Oh. So
they would get this perfect impact where you could set the camera right up on the whatever part of the rig they were interested in. Anyways, that was kind of the genesis of the interest in autonomy.
Huh.
But then kind of another kind of fun story about it was 2 years later, I graduated from undergraduate and started at a company called Gates in Michigan. Gates made belt drives, like serpentine belts and stuff.
My brother works there. Yeah.
Oh, does he really? Okay, cool. So I did some research and development in there. I was a big part of a project called AID, which was alternator isolating decoupler. It was this special alternator pulley that would isolate vibration and make the belt drive more efficient. I learned a lot there, spent a few years there, and then started realizing I was becoming a subject matter expert in belt drives, like a technical expert, getting really quite good at it on the different modes of vibration. And there's a lot there. It's interesting, but that kind of scared me. Actually, I was like, well, I don't know if I want to be an expert on belts. And so I went back to school to get a master's degree, still automotive focused, but then halfway through that, my vehicle dynamics professor, took us on a school trip to Continental. And Continental is a tire manufacturer. Everybody knows them for it, but they do a lot more than that. And they showed us an autonomous car they were developing. So Continental has a big ADAS and autonomy group. And it was kind of on this field trip, I learned about this. It was called HAD, or highly automated driving. So it was like a level 4 highway autonomy system. And this was almost 10 years ago. And I got so interested in the project that I ended up applying to Continental about once a month for the next year. I just kept emailing the hiring manager and saying, hey, look, this is some MATLAB script I wrote about this. And I read this paper about this and this, just to try to get into that space. I shifted my master's degree from automotive to mechatronics to be more suitable. And then a year later, I finally got hired into Continental after banging on the door for a while, and had just a great run from there out, developing autonomous cars at Continental and now at this startup called GPR.
What did you first do at Continental? So were you doing ADAS and autonomous driving systems?
Yeah, so my first job at Continental was ADAS test and development. So that was testing blind spot detection, which is like the little light that turns on in your mirror when somebody's in your blind spot, and then rear cross traffic, and then that stretched a little bit into ACC, or automated cruise control tuning. So that's where you're following the car in front, and I did that for about a year, and then I moved over to a group called S&T, which is Systems and Technology, and it was kind of the research and development group. And that's where things really got interesting. That was more 5 years out or more. So level 4 autonomy for lots of different applications. So everything from cruising functions to valet parking. So we made this amazing valet parking car that could navigate a multi-level parking garage fully autonomously. Extended that project into something called holistic urban driving. And that was where you would get out of your car at, say, a restaurant entrance, and the car might drive another mile through the city, find a parking garage, go and park in the garage, and then you push a button, the car would pick you up. I did a project called Cube, which was, oh man, that was such a silly metaphor. Continental Urban Mobility Experience, I think it was. And it was like this electric shuttle bus, and that actually ran in the parking lot at a few of the Continental facilities around the world and gave people rides from their car to the office. And then the last project I did at Continental was autonomous semi-trucks. So the Class 8 trucks. And I actually led that project eventually. It wasn't until after I left, but the work that my team was doing at Continental, that same team now is doing the joint project with Aurora. So the Aurora trucks are going to use some of the same tech that we developed at Continental.
Fascinating.
Yeah.
So you got your hands on a lot of projects there in, I think, 7 years.
Yeah, it was great. That was a great, Continental was a great spot for that because it was like every year and a half, some other, new thing. Intelligent infrastructure was another one. So intersections, putting cameras and lights and cameras and radars on intersections to make the intersection intelligent. That was a cool one too.
As an aside, do you have any tips for wearing down hiring managers for people who might be looking?
Yeah, I actually say this all the time. You're not done applying until they say no.
Oh, interesting.
Yeah, I mean, because it's, and hiring managers will tell you this. I've hired a lot of people as well now. It's so often you interview somebody, they might have been, really good, or you had follow-ups, and then your next meeting is about some fire at your company and you're working on this. Next thing you know, 2 weeks go by and, it slipped your mind because the interview was at 9 a.m. And maybe a really disciplined, organized hiring manager that doesn't happen to, but to a lot it does. And so if you follow up, if you say, send a note back and say, hey, what do you think? What's the next steps? And you don't hear anything back, that's a good sign. Typically when it's a no, they'll tell you a no immediately. There's no reason to hold, So I would say that's proven to be true to me. If you're not getting a response, or if it's an inconclusive response, it's because it's a difficult decision. And it can be a difficult decision to hire somebody. It's never a difficult decision not to hire somebody. So if you weren't a good fit, they'll tell you.
Interesting. I like that. Back to autonomous driving and a bit about your time at Continental. What are some of the interesting or surprising challenges when people are coming into this technology space, things they maybe didn't expect would be an issue, or problems that are maybe easier to solve than they might expect?
I think one trend I see a lot of that is problematic, I think, is sensor fusion or fusion of any kind. So fusion at its core, it's a good concept. And the way it's typically approached is you have multiple sensor inputs or multiple inputs to whatever system. Let's talk about automotive sensors. And each of them have their weaknesses. And the theory is that, well, maybe LiDARs can't do it on their own, and cameras can't do it on their own, radars can't do it on their own. But if we combine them together, then we have enough. Then it'll meet that. But it's not always that simple because there's a lot of shared failure modes between these sensors, meaning that if your LiDAR doesn't see it, your camera probably isn't going to see it, or if and so just sort of mindlessly saying, let's put more and more and more together, then we'll have a more robust system. I think there's some truth to that, but it needs to be more pragmatic than that. And I see that a lot with all types of autonomy companies of all levels of maturity. So all the way from the very complex, market leaders like Cruise and Waymo and Aurora, and down to the even the universities doing sort of smaller projects. This idea that we missed this detection of a pedestrian we needed, so just add another sensor there. Let's add an IR sensor now, a thermal camera. And I think that's something that really we need to do a better job of thinking through, because it adds complexity every time you do that. It adds new failure modes of each of the modalities. And it's not always that simple. And we see that a lot now with what I work on, which is localization. So localization is how vehicles know where they are on the HD map or in the area they're operating. And so traditionally it's just almost always done with some GPS system. So a high grade GPS or GNSS. And then we add sensors in to try to get the availability higher. That's typically how it's done. So they'll say, okay, let's now add in a IMU, like an set of accelerometers or gyroscopes to, deal with any errors in the GNSS. And then that starts to drift. So they say, okay, well, let's put in wheel speed so that we get, real speed measurement. And each one makes it a little better. And then eventually you're adding cameras and LiDARs trying to pick up features around the vehicle to use as landmarks. But I think you have these overlapping failure modes. And I think what we're going to end up with is a much simpler solution. What we do at GPR is we use a ground penetrating radar as a localization input. I think that we can greatly simplify how these things work sometimes by finding one modality that works really well. So you're not trying to take all these little pieces. That's something that I've seen quite often. And it's not just in localization, it's in a lot of pieces of the system. It's like, just add one more piece, and then you get from 99% to 99.5%. But then you still have 0.5% to solve, and you end up adding another sensor and another modality.
That seems like a trap for sure. I never thought about it that way, but as you say it, makes a ton of sense to me.
Yeah.
You mentioned some ground penetrating radar. Is that GPR's main focus, or what does GPR do and focus on?
Well, GPR, our company, stands for ground positioning radar. The ground penetrating radar, which shares the same acronym. Ground penetrating radar goes back, 50, 60 years. And it's a technology that's used a lot for surveying and archaeology. And what we can use ground penetrating radar for typically is detecting things meters under the surface of the ground. So you can detect, fossils and infrastructure and things like this. What we do at ground positioning radar is we use ground penetrated radar data for localizing autonomous vehicles. And our system that does that is called WaveSense. So the way WaveSense works is we can map an area where an autonomous vehicle is going to operate using our ground sense radar. So we mount this ground penetrating radar underneath an autonomous vehicle. And then when we operate that vehicle within a given operational domain, it can scan straight through the asphalt or the dirt road and create a signature of what's underneath the road. And then we can match that signature to a pre-existing map and get centimeter accurate localization or positioning of that vehicle. So one kind of use case where you could see this for level 4 cruising applications, so say a highway autonomy system, and this could be a semi-truck or a car. Currently, the way the truck, or let's say truck, stays in the lane is it's either going to use its camera to detect lane markings, and then it's going to position, or it's going to use a LiDAR to detect, the guardrail and signposts and things around it to position, or it's going to use GPS to position. And as I mentioned before, each of those modalities can fail in one way or another. So for example, the lane markings can get covered in snow, or there can be a layer of water on top of the lane markings and create glare for the camera. Sometimes if you're trying to use a LiDAR to detect features around the truck, if you're operating in a desert road, there just might not be any landmarks. There might be nothing around to use. Similarly, you can have other vehicles around your vehicle that blocks your sensor's view. And GPS can't be safety critical because it can be, of course, blocked by tunnels and things, but also just it can go down. You can't rely on it. And so by using data from underneath the truck, underneath the ground even, it's a much higher availability where the truck always can position no matter the weather condition. There could be 6 inches of snow on the road and it will still know exactly where it is. And that's really important as you move to those higher levels of autonomy, that you need to make sure your truck's always centered in the lane no matter what happens. And it's really becoming a factor now in that space, specifically the autonomous trucking, because NHTSA has come out and said that your truck cannot stop in lane or your car cannot stop in lane on the highway. So when we look at like Waymo or Cruise or one of the robo-taxis, if their localization system goes down, so if they have problems with their GPS or their cameras or LiDARs, they can just stop in lane. They can just bring the car to a stop, turn on their hazard lights, and that's okay. But for operating on highways, they have to continue until there's somewhere safe to pull over. And so if the truck or car is operating on the highway and a thunderstorm comes, they can't just stop and say, oh, I can't see the lane markings. They have to continue until there's somewhere safe to pull over. That's a huge, huge engineering challenge. Something I have firsthand experience with. Ground positioning radar is really a great solution for that, for the positioning.
You mentioned centimeter level accuracy, which is blowing my mind a little bit.
Yeah.
Is there enough variation in what's underground to like create a thumbprint of the locale, or how does that work?
I was surprised as well. When I first learned about the tech, joined the company, I was amazed at how character rich the subterranean data is. And when I talk to engineers in the space and explain how this works, that's always the first question is, because they know that if I can get real-time data, if it's character rich, meaning it's really unique, then it's really easy to position with. And it is. It's every centimeter that truck travels forward, the GPR scan coming back is extremely unique. And the best example of this is parking garages. So it works actually really well in a parking garage, multi-level. So it could be 7-story high parking garage where there's only sometimes 20 centimeters of concrete under the vehicle. And not only that, the concrete a lot of times was poured in a factory. They're called spancrete slabs that they build these parking garages from. And even within that, we're able to pull a very unique signature, just like you mentioned, just like a fingerprint or almost like a QR code, and use that for positioning to centimeter accurate localization. And yeah, it makes it really easy to work with.
Where does the data come from? I know there's like USGS data, but I can't imagine it's that specific.
Yeah, so it's map and track. So we have to map the area where we're going to operate in beforehand. And this is very common, actually. So almost all the autonomy systems, certainly anything level 4 or above, they map the area they're going to operate in first. Usually what they're mapping, though, is they're recording LiDAR data, camera data to see what's in the environment. And we do the same. So any vehicle equipped with WaveSense can map, meaning it can record what's under the route and save it. And it's actually a lot easier for us than it is for some of the LiDAR solutions because the data is so much smaller. So GPR data is a lot smaller. And a big reason for that is that its field of view, it's only 3 meters deep. So we're looking down in 3 meters. And that's not very much data compared to a LiDAR that might be looking 200 meters and 360 degrees. The other thing that's really nice about the GPR map data is all of it is useful. We don't have to filter anything out. So when you're recording with a LiDAR or a camera, you have to pull out all of the cars, everything dynamic, all the pedestrians. There's also just a lot of noise in the data. We don't have that. And so to map, when we want to map an area, all we have to do is drive it once at any speed with any vehicle equipped with WaveSense, and then we have that area mapped out in the tray to be used. And then any vehicle that operates there can actually expand that map. It can update that map. It can do change detection, and it's actually a lot easier to work with.
Have you found yourself becoming a bit of a soil science expert?
Yeah, no, I mean, we definitely get interested in it, but not to the extent you might think. So we're not super interested in what's underground or even creating a physical accurate representation. We just want to make sure that data is consistent for that area. And there's a lot of signal processing that goes into that, making sure that when the ground gets saturated with water, we can still match to it the same as if it's dry. But we're not particularly interested in how deep are there pipes or is the rebar degrading or so forth that most ground penetrating radar companies are interested in. So a lot of times we do see interesting things in the data, but we're just interested from the standpoint of, is that consistent? Is it going to change over time? More so than, is that actually interesting physically? So
you mentioned like water penetration into the ground. Is there anything unique about the radar or any frequencies that you've gravitated to help avoid that type of issue?
Yeah, it's a good question. So our frequency band we operate in is 100 to 400 megahertz, which is pretty standard sweeping frequency for ground penetrating radar. We have to notch out some areas for FCC compliance, but in general we use that whole band. And typically the lower frequencies penetrate deeper. And so depending on they're also lower resolution though. So the lower the frequency, the longer the wavelength, and the harder it is to get high accuracy. So we are doing this balance between using the higher frequencies to get the high accuracy, and then the lower frequency to get the deeper penetration. The deeper penetration typically is more robust to to water and to surface things on the surface like snow and puddles and things like this. So it's a kind of constant balancing act, but all of that filtering is done in real time, to account for that. And it's also not as simple as just using the GPR image. So we're not just taking the data and directly using that for matching. We're running, a series of filters on it, a series of feature extractions. So we're not just trying to take the data in its raw form. We're pulling out almost like the same type of features you pull out going into a convolutional neural network, like a convolutional layer. And we have lots of engineering that goes into that. And that makes sure that even if the ground gets wet or there's small changes to the ground, that we're always able to match. That's been the subject of years and years of research from our exceptional engineering team. I've been very impressed with our team in terms of their ability to solve this.
That seems like what must be a bit of the secret sauce is how you take that data from the radar and match it up to an existing map in a way that doesn't use too much bandwidth and is computationally available.
That's exactly right. I mean, if you talk to companies that have been doing working in ground penetrating radar for years, they almost always say, no, that wouldn't work. Guys may say, no, the data changes way too much from moisture and and that's been their experience. But through a lot of the signal processing you do and the kind of calibration, the real-time calibration, and it's also to add complexity, we have to deal with sensors at different heights. So sometimes we map with a sensor that's 10 centimeters off the ground, and then we'll localize with a sensor that's almost a meter off the ground for mining. And so that creates a big difference in the radar return. We have to normalize that. Different vehicle speeds, the speed of the vehicle can have an effect on the radar return. And then of course the soil density itself, there's compaction, there's motion. Yeah, no, it's still a lot easier to work with than LiDAR data, I can tell you that.
Interesting. What are some of your favorite solves? Like this was a roadblock you ran into and how you got through it?
I think one good one that the introduction of really a lot of convolution and feature extraction to the GPR data has enabled is what we call omnidirectional localization. So the problem we were facing before was that we typically, when we would map, say we built a map track that was north-south, so you're in most cases it actually wasn't a problem, but for some cases it was. You were headed north-south while you mapped. When we localized, we always needed to be within plus or minus 20 degrees of heading of that, meaning that we could go, just a little bit off and north, 20 degrees to the left or to the right, and still localize. But we couldn't go more than that because getting the matching to work was a problem with some of the calibration and some of the signal processing. And it was something that we were really working on solving by trying a lot of complex methods, and then the introduction of kind of convolution and creating a featurescape instead and matching on that. It decreased our map size, it made the matching more efficient, and it allowed us to localize going east-west on a map that was built north-south. So that means in an area like a seaport where we have a lot of applications, we can map doing a bunch of north-south drives, almost like you're mowing the lawn in the seaport, and then we can have autonomous vehicles drive anywhere. That was huge. And we had some really exceptional engineers at GPR, test that, implement that, get it to run in real time, which was really good. And that was quite recent. That was about maybe 8 months ago. Testing started, and we just did the full feature release on that a few months ago.
The amount of matrix math that must go on on your team is mind blowing.
And it runs on a very low compute as well. That's really key. So I think we're using a single core of a Intel Crystal Lake, I think it is. Yeah.
Wow. I assumed you were going full FPGA or ASIC with this, but it's running single core.
It will.
Okay.
The early signal processing, I think, is FPGA based, and but the matching part, and then also there's a real-time change detection, where we're kind of monitoring the map to see if it's changing more over time. That's running on Intel processor now, but we'll also be able to port that to other processors in the future. So that part of it, the matching part, is called NavSense. And there's kind of three places we can run that. One is we run it on external compute, which is how we do like our eval kits. So if a customer buys a system, they want to test it, we ship a computer with it that's already set up. The other place is that we can run it on a CPU on board the radar itself. So have like one fully encapsulated radar. And I should mention the radar is very thin. It's only about a little over an inch thick. So there's not a lot of space in there. And it's a very harsh environment under a vehicle. And the last place is we can run it on the edge of the customer's compute. So if they already have a big compute stack, doing other signal processing, we can run the NavSense on the edge of there. And compared to a lot of the other camera and LiDAR radar processing, the GPR is much, much, much smaller.
Yeah, that's tiny.
Yeah.
That's really small.
Yeah.
I'm thinking of the word like integration hell, and thinking of how much you've talked about, sensor fusion and tacking on new parts. What does integration look like for GPR, and how have you avoided some of that, traditional, multi-company, multi-vendor product integration challenge?
The GPR output will almost always be fused with other localization modalities, either for availability, for redundancy, or sometimes just for simplicity of the customers are already working with other inputs. The most common one is GPS. So GPS, there's like a high accuracy, high grade version of GPS called RTK, which is real time kinematic, and it can offer 2 centimeter accuracy in open sky, good conditions. There's a lot of caveats to that. You need real time corrections through a cellular network or something, some way of getting those real time corrections. It can change pretty dramatically depending on multipath. So if the signals are bouncing off of trees and buildings and things. And so it's not very high availability. And a lot of times it can give false confidence. So it can say your vehicle's within this position within 2 centimeters, but really you're 4 meters away from there. That's one of the unfortunate side effects. And so there's a lot of expertise in fusing that output with other outputs. The other big output that every system, and our system always needs, is IMU, or these accelerometers. So the way the IMU works, it's a relative measurement, meaning that the vehicle had its last coordinate, some period of time goes by, you take the accelerometer data, and you can extrapolate your vehicle's new position. It's almost like a vehicle speed and a heading, and you apply that in your Kalman filter to have the vehicle move forward. And then the GPS can be used as a global correction sort of update. The GPR system similarly can be used to update that position. And in a lot of cases, we would go to a new customer and they would have their current localization fusion that was almost always based on GPS, IMU, and then maybe they have a camera or a LiDAR as an additional input, a camera LiDAR match. And they had whatever fusion there. And they would either ask us to, one, replace everything with just a GPR system. And then what we would do is we put the GPR system in, but we would also put in a INS, like an IMU with a motion model, and then maybe a GPS system, and then try to show a complete solution. But the problem with this is that to set up a motion model and a GNSS system into the customer's vehicle, we were spending all this time showing them things that weren't our core technology, which is the GPR, and a lot of times fighting it. So the filter itself would be fighting between the GPS giving poor positions and the GPR giving good positions, and we're trying to resolve both, and it was bringing down ours. So now the new approach that we've been doing for about a year now is we have a couple partners in the GPS space or GNSS space. And with these partners, they have the competency and the years of experience making INS GNSS filters. So they have already a full setup where you can buy these systems. They come with a high grade GPS and then different grade IMUs. And we natively injected the GPR into their system so that it can be purchased as one piece, and it's sort of a plug and play drop into a customer application. And this is good for 2 reasons. One, we can get customers working almost immediately with the GPR, and they get the high availability, and the system just works out of the box without a lot of integration. And then later, if they want to just work with just the wave sense and then, do a more base level integration, we can do it at that stage. But there's definitely something to be said about early on trying to integrate a lot of different pieces just to do a proof of concept with a customer and then being held back by the limitations of the GPS system and it blinding the customer to the value of the GPR. Maybe someday we end up providing a full localization fusion system, but right now we're going to let our partners do fusion or let the customer do fusion, and we're just going to work on making the GPR an extremely high availability, robust input that makes their fusion work better.
Yeah, I'm a big fan of doubling down on what you're good at. I think that's the way to go.
Yeah.
What else is going on under the hood that makes GPR work?
The last piece of the WaveSense system is called MapSense. So MapSense is a tool that can take the WaveSense data from all of the different vehicles that can collect it. So at the beginning, usually we have a mapping vehicle, which is like a survey vehicle that can map an area. So it's say a seaport or a mine site, we would map. And we take all of that data and we inject it into this tool MapSense. And we can apply post-processing corrections or map smoothing or stitching or even fusion, where we can stitch together all of the GPR data into one coherent map. And MapSense can also take in data from the localizing vehicles. So if you say you have your fleet of autonomous mining trucks running, and one of the WaveSense systems on one of the mining trucks detects an area of the map that's degrading or is changing, that data can be uploaded to MapSense, and the map can be updated using the localizing data. It's like a crowdsourced build. And the MapSense tool has a lot of development in it. There's kind of two places we can run it. We can run it on the cloud, which is great for a lot of on-road applications where you have a lot of data coming in from hundreds of vehicles, or it can run on an individual developer like an on-site server. And that's important for certain applications where they don't want any external connectivity for security reasons. So like the seaports, they're not interested in having their autonomy systems tied to the cloud. They want everything on premise. And so MapSense can also run locally, and they can update their maps, build their maps out without any need for connectivity. And that tool is becoming quite powerful as we're adding the features into it.
It's like Waze, but for ground penetrating radar.
Yeah, sort of. Yep.
So you mentioned seaports and mining a little bit. When I think of this sort of autonomous driving technology, I think of maybe long haul trucking or eventually consumer level product. But what are some interesting applications where autonomous driving is being especially useful today?
So the commercial space is where we're seeing the most traction. And I think part of it is that GPR is a really good fit there, but also that's just where the autonomy is being the most successful overall. And there's a few reasons for that. So a lot of times people ask me, where are we going to see autonomous driving first, or when are we going to see autonomous driving? And it's almost always where the operational area is dangerous and it's really expensive to operate. And nowhere is a better example than mine sites for this. So mine sites, often they're extremely remote. They're somewhere that is not a good place to live for one reason or another. So it can be very expensive to pay people to operate these vehicles. They're also very hazardous environments. Either there's lots of dust and carcinogens in the air, or it's just there could be cave-ins if it's an underground operation, or the pit mines can be very deep. The trucks themselves can roll over. And so there's a lot of interest in automating these vehicles. And actually in the mining space, both Komatsu and Caterpillar have had autonomous mining vehicles running for well over 10 years. So one of the earliest applications of any kind of broad autonomy. And they face right now a big issue, especially in South America, called ionospheric scintillations. And these are solar storms that actually block GPS or interfere with GPS, and they can make their entire fleet of autonomous vehicles go down. And when they go down, it can cost sometimes millions of dollars, a month in downtime, just because these trucks are so huge and they're moving so much material. And so there's been a big push to try to solve that. And that's why the mining have been very interested in applying WaveSense as soon as possible. Seaports is an interesting case as well. Seaport is another spot where there's a lot of benefit to autonomy for the same reasons that those areas can be hazardous to operate in. Cranes loading containers and things onto these automated guided vehicles in seaports. And it's also areas where they don't want mixed operation. So if the cranes are automated, they don't want manually driven trucks. And so they try to keep everything automated. And up until now, all of the localization in these seaports has been done using infrastructure. And the infrastructure is these transmitters that they actually install in the asphalt. So they drill holes in the asphalt every meter or so, tens of thousands in one seaport. And then there's sensors on every vehicle that detect these transmitters. And that can't be done at every seaport, so it's limited where the automation can be. And then it's also very expensive to do that. So the waste that's being applied there as well. To the long haul trucking, that's another application that's quickly getting momentum. So if you compare the long haul trucking to the robo-taxis, the long haul trucking, I think, has a big advantage on business case for a couple of reasons. One is the truck drivers get paid a lot more. It's a much more difficult job to operate a truck than it is to operate a robo-taxi. There's a shortage of truck drivers, which can be, also a motivator for the autonomy. And also, you can run the same simple route with an autonomous truck every single day and be making money. It can go from here to there. You can map that route. You can really make sure it's secure and just keep doing that route and be making money. In the robo-taxi space, the dollar per mile is a lot less because the operators of taxis are a lot less. And then the routes are a lot more dynamic. You can't just go A to B with a robo-taxi. It has to be able to drive all over. So we'll see a lot of the long haul trucking coming up sooner. There is like that unknown, I think fairly unknown reason that the trucking's a lot harder than the robo-taxis, which is that fallback path or minimum risk maneuver I talked about, where the trucks have to continue if there's a problem and then pull over, where the robo-taxis can just stop in lane. That's not trivial, so they're still working on that, I believe. So we'll see that as well quite soon here. But the mining, the seaports, the long-haul trucking, those are the spaces that autonomy is really being applied quickly to. We have customers in each of those spaces.
From your perspective, what is the state of autonomous driving today? What's the general net sentiment? How do people feel about how capable it is? And does that align with the reality?
Yeah, that's a good question too. So I think we're kind of through the hype curve. We had this really high hype a few years ago.
Yeah.
The hype hit hopefully bottomed out last year. And now this kind of realization setting in of, okay, where's the tech really at now? Where's the regulation really at now? Where's the business case? And the companies that kind of made it through that, because a fair amount of companies closed in the space in the last few years. The companies that made it through, they have real business cases. They have real vehicles that are operating on roads. They're not sort of waiting for some huge breakthrough.
So the tech is there, and these companies are able to build a real thing.
Yeah, so these customers, they have their MVP 1, their minimum viable product 1, which especially in the trucking space, we're going to see really simple routes, like just desert roads, probably not a lot of traffic, not a lot of complexity, no adverse weather, so no rainstorms, no snowstorms. And then once they get that working, they'll probably rely on their next, as they're scaling to their next phase. There's two things we'll see. We'll see a move to more commercialized hardware. So moving from kind of research grade, LiDARs and cameras and compute that are very expensive to more automotive grade. That's where like Aurora's partnership with Continental will come in. We'll start seeing them use automotive hardware that they can build cheaper, more reliably. And they'll start expanding their ODD or operational design domain. So they'll start trying to move that technology to the Northeast where there's snow, where there's adverse weather. And that's really the big shift is the questions are moving from, is autonomy possible anywhere, to is it possible to build a business case around this? I always say the much more interesting question is there's a big difference between getting a Waymo to operate around San Francisco and then to actually make money doing it. Because those, Waymo is impressive tech for sure, but very, very expensive. Very expensive.
Yeah, and the San Diego to Yuma or San Diego to Phoenix trekking route is not likely to have snowstorms they have to deal with.
No, that's absolutely right. And most of the operations will be in Texas, I think. And a lot of that has to do with the regulations as well. So Texas has been very supportive, where I think California less so recently.
Yeah, I'm always curious to get people's perspective on Tesla's approach to autopilot and their general philosophy of EVs and AVs. Usually it's an off-the-record conversation, but is there any thoughts you can share?
I think Tesla, it's something something that frustrates me is there's a lot of people that like to speak in absolutes about it. And what Tesla's doing, no one's done at that scale before. There's nothing even close. The amount of data that's going into their end-to-end machine learning model is, first off, the mechanism, the machine they built to do that is amazing. Just absolutely amazing that they have literally millions of vehicles operating, sending the data into this huge, what do they call dojo, I think it's called. And then all of the training data, the corrective training data is actually from their customers. So when you're like grabbing the wheel and telling the car what to do, you're training their network. And so when people say that's not going to work, it's like, look, there's no way that's not going to work. And there's also no way to know for sure that it is going to work. So as an engineer in the space, I just find it amazingly interesting to see. The other aspect to it is, around their vision only, right? They're only using cameras. And there's also that mentality of, people saying, well, it's impossible to do it without LiDARs. It's possible to do it without radars. And that's also like, we all drive cars with just our eyes. We can't ignore that. The roads are built for eyes. So there's something to be said there. But at the same time, radars are so effective at seeing through fog and snow and adverse weather, and they're cheap and they're reliable. It is kind of questionable that they're not using it. But I think that I find it very exciting that Tesla is doing something different than everybody else. They're not going to have a business model problem because the cost of their system is, maybe it's not cheap, like it's not $100 for their autonomy system, but it's cheap enough that it comes with every car they sell, regardless of if you buy autonomy or not. That's pretty impressive. So I think where we're going to see Tesla struggle likely is getting the long tail figured out. So the fallback path of when you have full self-driving, or they call it full self-driving, but it's really level 4 with a big operational design domain. What that means is that there's no situation where the vehicle can be unsafe. So the way they're approaching it with this totally open operational domain without a lot of mapping, meaning they don't have a lot of areas sort of set aside that these are safe haven spots or places to pull over on their routes. I just think that there's so many things that can happen on the road that might be really rare for an individual. So I use the example of like a flooded road or a vehicle that's on fire, or an accident that happens in front of your vehicle. It might only happen to each individual once in their lifetime, and an average human drives 500,000-600,000 miles in a lifetime. But you're talking fleets of tens of thousands or hundreds of thousands of vehicles. These are things that are going to happen almost every single day, and those are really hard to test. It's really hard to get data of a flooded road. So, for example, if the road is covered in water, knowing if it's safe to drive through that puddle or not, that's something that's going to be really tough to deal with. And so, even though the full self-driving has gotten to the point where there's not that many disengagements and it seems to drive really smooth, the question is about those edge cases, those once every 1,000, 10,000, 100,000 mile incidents. And just by the nature of they're rare, it's going to be really tough to get that training data. So, it's just really exciting to watch. I think Tesla, it's really exciting to watch. They're taking a huge gamble on how they're approaching it. And like I said, anybody that says it's not going to work with any kind of confidence, I have to kind of roll my eyes and say, you know what, like, what are you comparing it to? Yeah. Like, all the other, broad scale autonomy, there's nothing to compare it to.
Yeah, I like that perspective a lot. Thank you.
Yeah.
Thank you. So it sounds like the tech is changing fast, and there's still a lot of engineering challenges to work out for people who might want to get started in the field.
I always like to say too, like, if you're interested in the space, I think it's an amazing place to work. Every year that the industry shifts so much, there's new tech that comes in, new applications, and I kind of have this running joke with my friends in the space that we'll have a long career getting autonomous vehicles on the road. It's for all of the predictions of, I think the first prediction when I started was like 2020, for some of this stuff. And now 2025, well, now just no company is stupid enough to start throwing dates out. But for a while, we were, even at Continental, we were throwing out dates, and it was, so it's an amazing place to build a career. So if it's something that interests you, yeah, definitely pursue it.
Well, we like to do a lightning round at the end of these. Quick questions, quick answers. Other than ground penetrating radar, do you have a favorite sensor technology? Doesn't even have to be autonomous driving, just sensors in general.
I think thermal cameras are really cool. I haven't worked with them massively, but the times I have worked with them, I've been just really impressed at the contrast you get, especially obviously on pedestrians, but even on cars. There's a pretty good strong thermal image. And I'm sort of surprised we don't see more of it. I mean, there is some. I mean, FLIR is getting a lot more involved in the ADAS market. There's some production cars that are shipped with it, but I think even a lot more can be done with it. I'm wondering when I have to look into it. Maybe it already exists, but getting camera ISPs that can work in the thermal band, but also the sort of the color bands. And yeah, I think that's a really cool sensor technology. Also 77 gigahertz radars. So, Continental has one of the best 77 gigahertz radars. And I was really impressed at how well that could work. And then some of the extrapolations of what you can do with that, I think is really quite interesting.
Yeah, the millimeter wave systems are quite the feat.
Yeah,
for sure.
And they keep getting better and better and better. I just saw it AutoSense yesterday. This company Zendar, and they're using millimeter wave radars, but they move their transceivers kind of farther apart to get almost a stereo effect. And I thought that was a great idea. I think aerospace does something like this for phased array radar. But I think that'll be really cool. I think that'll get the accuracy even better at the hundreds of meters range that's needed. Yeah, that's another kind of interesting edge case, or not even an edge case, but just a challenge for the autonomous trucks. They have to see so far ahead, and they have to see road debris so that they can move, out of lane. And one really hard thing to detect is tires. So tires, LiDAR struggle with, because rubber really absorbs a lot of the LiDAR. And when you're talking about seeing something 300-400 meters ahead of the truck, your azimuth accuracy has to be really good, because a tire sitting on the shoulder versus a tire in your lane is obviously a big difference in terms of how the truck reacts to it. And the trucks slow down so slowly. So being able to detect objects in lane hundreds of meters away, I think millimeter wave radar is probably the best approach. And it's always like the other big challenge is can you drive over it or not? So like a tin can, that's something that you could drive over.
I hadn't heard about tires being a LiDAR challenge, but that makes sense. A tin can, safe to run over. A tire, not so safe, but maybe hard to tell the difference.
Yeah, it's something the LiDAR industry tries to hold back.
Sure, it's like, don't tell them.
Yeah, tires are tough. And then the other example was the soda can. So a soda can on the road, and that can be tricky for radar, because it can show up as a fairly strong radar return. And if your radar doesn't have the ability to detect elevation, that could seem like a big problem, and really you can drive over a tin can. So
sure,
there's a lot of complexity there of how to deal with road debris.
And then the last question, you mentioned as a kid you were just into machines and vehicles overall. Do you still have a favorite vehicle, like all time great?
Favorite vehicle? Wow. Well, I should say I have a pretty big shop here in Michigan, so I have all kinds of things. I have a machine shop with welders and a mill and a lathe, and I build all kinds of stuff.
Yeah.
Right now, my favorite vehicle, I have a 1970s bulldozer.
Oh, that's cool.
It's called a Dresser 100E, and I've made all these modifications. So I made this thing that goes on the back for dredging out my pond. So it's an old crane boom off a Grove crane, like the jib portion. Yeah. I have this winch system, and so I can back up to the pond, drop this in, and then put different tractor attachments and sort of clean out the pond. That's one of my favorites. I really like that machine. It's very mechanical. It's easy to work on. It has a new Cummins 4BT in it. That's a cool machine. Something newer. Last year, my wife, I got her a Mustang Bullet. So the new Bullet Mustang with the 6-speed manual. That's a really fun car. She doesn't let me drive it often, but when she does, I enjoy that. So yeah, those are two.
Amazing. Those both sound like dream machines. Sadly, Noah, we're out of time, but thank you for being here today.
Yeah, thank you. It was really fun. Great questions. Yeah, love the podcast.
That was Noah Gedrimas, VP of Strategy at GPR. What a fascinating dive into ground penetrating radar technology. I get so excited when I think about how autonomous vehicles are becoming more and more accessible, and it's a treat for me, and I hope for you, to get a peek at the tech making it happen. If you like this podcast and you've already subscribed, please share this episode with a friend or coworker that you think will like it too, and share it on social. We'll have a post up on the Moore's Lobby social pages. When you do that, you are helping this podcast grow and get better and better. Thank you for joining me today in the lobby. I'm your host, Daniel Bogdanoff, and I'll catch you next time.